Right, so come in, Haruka-san.
May to take the picture.
Oh, God. Okay. Toa?
Okay.
Sorry, thank you. Come. Right. So it's my pleasure to introduce those present to this presentation in memoriam of the father and grandfather of, respectively, Hiroka-san and Toa. And I had not heard of Dr. Takaaki Matsumoto in all of the presentations and conferences and papers that I had gone to since 2012 at all, not one mention once. And it was in Sochi on October the 5th, as I recall, 2018, when one Russian scientist mentioned this researcher called Takaaki Matsumoto, and what he was showing is something that we had seen in our experiments. And I thought, there's someone as crazy as me. So I would like to investigate this guy. And it just so happened that I'd gone to Aarhus University, and this guy called Dieter Britz there had been keeping a record of all of the papers that were published in mainstream journals, predominantly fusion technology, in the early years. And he had given that to me when I had visited him a couple of years previously to go and work with Aarhus University. And I knew that it was likely to be in there because anyway, so I searched and I started reading the papers and I thought, oh my, we've actually replicated several things. Thank you. That were what was in those papers. And so I felt that I needed to investigate this guy's work more. And I was told that he'd died in 2013, and that was a real downer for me. But what I found was, of the available papers online, there seemed to be other papers that were not readily available. And so my good friend Sho, who's trying to sit down and hide, come up here, please, come here. Shojiro here, he invited me to come and test Dr. Roishi Namaza's technology in 2019. And that was absolutely and totally critical for me to understand how many systems in LENR work, and more recently in Binchuan Huang's reactor. When you see things under the microscope, it was totally demystified by the contributions of Dr. Roishi Namaza and by Dr. Takaaki Matsumoto. And this came about because of Sho's reaching out to me.
To Japan at that time.
Yes. And so I reached out to Sho and I said, look, I need this guy's papers. Could you write to Hokkaido University and see if they've got any on file? And I'll let you take over now, if that's okay. And I'm going to come and stand next to you, excuse me, so you can hear the mic. Right, there you go. What happened? You wrote to the university and...
Yes. For the 2 months or no, they answered no connection. I mean, he was retired very, very earlier. So then some of the staff at the university wrote, sent my message to Dr. Matsumoto by mail. And Dr. Matsumoto read that, my letter. And then he was very glad to find there was someone who was interested in his work, and he sent me this kind of book. He made this kind of book at that time
200 copies. He self-published 200 copies.
Delivered all the scientists at the conference, but unfortunately no one paid it.
In which conference was that?
10 or I don't know.
In one of
something
the
like
ICCF.
yes,
Okay.
yeah. And that is where the Russians had got their understanding of his work. And it was cited actually by Russians in, like there's is it Boldarova or, anyway, there's a couple of papers that cite his work with regard to some of the tracks that were observed in the early 2000s, but in Russia. But that's it. And I only found that out through looking into the work.
Mm-hmm. And he sent me one of this copy, and then I sent that one to Bob, and Bob received the book, and he was very, very surprised.
Yeah.
And he made this remaster.
So this is a one-for-one copy. So that the original book, which there was no files to build it from, so I had to scan and OCR and correct, and also because Dr. Takeaki Matsumoto's printer had a problem. It was striking through the several last chunk of the book, like the last third. So I manually took almost a day to remove all of the bits of the letters, so that I didn't want to OCR it and just print with new text. I wanted it to be an authentic one-to-one copy as best as possible. So that was that, and we put it out as a free PDF.
Yes.
And I think it's been downloaded thousands of times. And I know the book has been sold, which I can honestly say we make about 2 cents on each copy. It's basically at cost. And in fact, they've written to us and said, like, you might have to raise the cost of the book because it costs us more to print now. It is still $10. Yeah, yeah. So
you can buy at Amazon.
Yes. But it was very clear that we needed the extra materials, and so. After doing this, I then I came to Japan,
Mm-hmm.
and we were, because you said, come over here, move along, Tara. Come in. What's happening? Oh, he's asking to move the panel. We've been naughty boys. Yeah, okay. So you take over now. So. You had suggested that you had some videos and that maybe we should come and look at them, and because they were going to be thrown away otherwise. And so we came and some materials. We didn't know how much, and so we came, and I found out that there was these videos. We just thought it was going to be some documents. And you came over in a couple of times, like one was a few documents, and we scanned those, and then it was like you brought around a few videos. And, we're going to need to get so we had to go out and buy the equipment to capture the videos because we couldn't keep them at that stage. And then we had to buy an old 2 NTSC video recorders. And fortunately, I actually built a business for a friend many years ago in transferring videos to DVDs and so on. So I actually knew exactly what to do. And so I didn't sleep basically for a week because suddenly there was a lot of videos that we could capture. So we captured those, and we have the videos, and they're all going to be published. And it's incredible resource. It's a unique type of research. And after we did that, you suggested we come back another time, and Dr. Matsumoto and yourselves organized all of the materials that he had. And when I turned up that second time, it was a complete shock because it was a very large amount of material. it was filling 1/3 of a room, right? And so we scanned what we could, we took what we could. There's still some materials that we're now taking, and some of those are what you see around the room, a very small fragment of them. So I think we have all of the materials to make the best possible version that could be made of this book, which is totally been OCR'd. All of the English has been completely corrected. All of the mathematical equations have been properly put into LaTeX, everything. So it'll be a pure PDF, and it'll be a very, very high quality print document. So thank you very, very much, Morioka. And Toa, actually didn't really know your grandfather, did you?
Not really.
Not really. And so he's been having a baptism of fire probably more than some of the people in this room, right?
Yep.
Yeah. So he's as curious, I guess, maybe even more curious than you guys to learn. So let's do that. But do you have any memories of him?
Yes, I have.
What would you say?
Well, I'm
Not to put you on the
say-
spot, but I'm putting you on the spot.
Yeah. Well, my grandfather almost never taught about those like equations and stuff. So, well, we were basically just like playing around, just drawing pictures and then stuff.
Oh,
yeah.
that's perfect.
Nothing scientific.
Nothing scientific.
No, not really.
Yeah, but that's what he should be doing with you, right?
Yeah.
Not trying to,
Too
you know,
late.
show you old pictures of experiments. That would be boring, right?
He did it to me.
Ah, okay. And what did you think?
Yeah, again, at the dinner, he explained those natto model,
Natto.
Yeah.
80 natto, and he started explaining again.
Oh, not again, Dad. Yeah, okay.
So we didn't think it's a great thing, but
Yeah.
after he passed away, Rob found those stuff and really
Precious.
good. Yeah, precious. He said. So I'm really appreciate and thank you so much for coming and as well.
Okay, so pressure's off. You can go and sit down
Okay.
now.
That's good then.
Okay, so this is the man himself in 1992, 16th 5th, 1992. The wonderful thing about Dr. Matsumoto is he took a little bit of a photo diary. So these are sort of around the transition period before going into Lena and after, where he's traveling around the world, going to linear accelerators and so forth, because that was his meat and potatoes. And so over there on the first part of the table, there's a couple of books and resources out of the big library of things that were relevant to his studies in research, nuclear research reactors. You can see gamma transmutation, you can see transmutation of actinides, you can see neutron optics, neutron scattering books. So he was doing all of this mainstream nuclear science work. But one thing that he was clearly an expert in was radio emulsions. And so this actually is a link to the Kickstarter for the book. If you want to contribute, that would be fantastic. But he focused on doing simple, novel, cheap, and quick experiments. And so this one, when you see, we actually have photographs and video of the experimental setup. And he was utterly meticulous. So we have each experiment is given a code. Each experiment has all of the listed components, even labels from the reagents used, the molar concentrations, the times that the different currents were applied, absolutely everything like you would expect from a really methodical, good scientist is in there. And then he also does the same with the analysis. But this is a large titanium bolt in an electrolyte solution. And he has a large variac, you see, variable transformer. And he might be putting it through a chopper bridge to make it DC. I think it was AC in this case. And you can see the experiments. We've got videos of those. And if you swing your head round, right at the back here, and we'll return to this later, you can see these electrodes. And he sometimes it has them the other way up. And here you can see increasing close-ups on them.
And what were the voltages?
I'm going to talk about that shortly. Well, a little bit later. But everything, you'll know how to replicate these experiments precisely. So that's just a quick aside. So what you can see here in this frame here is his unique use of stacked nuclear emulsions. And in the Cold Fusion Conference in Strasbourg last year, I stood up in front and when I gave my speech, I asked my first question, does anyone in here know how to use nuclear emulsions? And there was dead silence. I said, does anyone in your team have any level of competence in the use of nuclear emulsions? And 0 people put their hands up. So we're living in a world where we're supposed to be doing experiments into nuclear reactions, and no one knows how to use nuclear emulsions, which is just the meat and potatoes of doing the science that led us up to the nuclear age, understanding it. And so what you can see here is a single lead brick with 1 pack. Now, what is this? These are A4 sheets which have got the nuclear emulsion on it, and there's many emulsions in there. And so this is a whole pack of emulsions. And he has 1 lead brick, no lead brick, 2 lead bricks, no lead bricks, offset, and then some in here orthogonally, right? And when you look at his diagrams for his experiments, he lines them like that. And when you look at how he does the analysis for like the gravitational waves and other things in there, it makes sense when you can see the pictures of how he laid them out, the experiments, where he draws a line and says, this is where these emulsions were. And
you going to explain something more on nuclear emulsions, or what is this nuclear emulsion?
It basically is able to record X-ray tracks, alpha, beta, these kind of things.
Okay.
And so he knew what you would normally see in all normal nuclear interactions, right? So he knew what a muon catalyzed fusion event would look like. He knew what an X-ray little track would look like. So he then did deep analysis of the resulting materials. So this is a wet film camera that's looking as part of the scanning electron microscope, because that's how you imaged it back then. You didn't have a CCD element taking a number of pixels and doing a scan.
So we took these sheets and went to some pure sources and recorded the tracks, is it?
You develop the film and then you look at it under a microscope, and you look at in the book you see examples, but there are vast numbers of samples. I've got some samples over there that you can see of the kind of things that were observed on the nuclear emulsions. Okay, and if you want to lead this field, there's a whole area that really gives you insight about what's going on that no one is doing, right? I did a bit, but I only looked at little X-ray, dental X-rays you get from India.
So that's what we have tried that.
Yes. Yeah.
But they also react to moisture and fuel.
Yeah. This is the proper way to do it.
Okay.
Proper nuclear emulsions. You find out how to get them properly developed and so on. So he lists the type that he used. I think it was Fuji, whatever, and so we actually have these as well. So I'm going to see, as the process moves forward, if we can rescan them and take what he saw, but see it at a much higher resolution with more modern scanning technology. But anyway, so for instance, he used these large format ones, but he also used 1 by 1 inch or ones, and then he would divide it into 4, and he would spend a whole day looking at 1 inch square. And he would write down in his analysis logbook the things that he saw under the microscope on the emulsion, and then he would draw the XY grid reference on there, and then take a photograph through the microscope into a wet film. So you have wet film resolution only limited by the optics of the thing and analyzed with a microscope objective, giving you a large insight into what's going on. Just attention to detail is phenomenal. Now, there's a big problem with this because he had to take these, which we actually have, which are medium format negatives, right? They're like this. So they're almost 4 times the size of a 35mm frame. He had to scan those or develop pictures and then would photocopy or whatever he did. And that's how he ended up with things that he tells you it is this in his book. And frankly, I just couldn't see it. And I'm pretty good at seeing stuff where other people can't see it. And I'm just going, not even with my best abilities can I see what you're trying to tell me is meant to be in this image. And so let me find what I'm referring to here. It's here. So here, this is meant to be a partially decayed product, right? And we'll come on to what that is. I can't see what that is. It's just a black blob in a bit of a mess. And over here, these are meant to be ring clusters, and I can't really see them. I can see there's some slightly circular things. Well, look what we got here. And this is, I could print this the whole size of this page as well. Yes, it would get fuzzier, but actually you've got the gradient in the film. And also, this can only display CMYK 8-bit, right? But actually, I'm scanning it at 16-bit, so I can see all of the detail in the highlight on this bit, which you can't. And in digital capture on an SEM, you're fixed at the resolution you choose and the bit depth you choose, and that's it. You're done for all of time. So we've been able to convert what this is completely unreadable. But how about this? That compared to that. It's a completely different world. So we've ripped this from the past and brought it into the future in better imaging capability than many people can do today. And we'll talk about that in a little while. Okay, so that is imaging. And then he pioneered this. I thought I was doing something original, but I'm always sure that someone's done something before me. And I wasn't surprised to find that your father had done this unique thing. So he has his cold fusion experiment in here. He has a very high quality video camera here. A front attached to that, he's got microscope plan objectives. So he has a 20 times or 200 times microscope objective, so that he is looking at a very small area. He's only got 640 by 400 lines at 60 hertz interlace on his video frames, but he's only looking at 3 millimeters in his field of view. So he's got like a 12K video at 60 frames a second, recording the bit that he wants to see, right? He's doing what you normally do now with high-speed cameras. You actually have a sensor that's very big, but you actually only use a very small part of it. And that's not as good as what he was doing, because he was magnifying up the bit of interest and recording the full frame of it. And you can see it here. You can, if I plug myself in, right. So in this image here, you have, this is 1 millimeter across, palladium electrode, okay? And this, you'll see, is the experiment. So he's moving from 0 volts up to 40 volts. And as you go up to 40 volts, the evolution of gas increases. Increases. And what he notes in this paper from 1996, shows so many pieces of data that people think they have found since. It's a literal gold mine, this one paper that's in the book, right? Now you can see he's getting up towards 40 volts and it looks absolutely insane. And then what he notes, that between 40 and 70 volts, that there is what he calls a pinch effect. So you can start to see sparking coming on at the end here. There's a pinch effect where he says that causes suppression of the evolution of gases. But you have to remember that he's also saying that there is something in the base of this electrode that is causing clusters of hydrogen. So the hydrogen isn't becoming hydrogen gas, it's becoming bound into a cluster. Okay? So now you start to see the suppression of the gas evolution. And there was a Chinese author, and when you actually slow this down, you literally see these explosions, literally like nuclear bombs going off, and the hydrodynamics coming off, and sometimes they're coming out into the water.
Cavitation.
Yes, it's cavitation, but you have the plasma in the cavitation structure. He has other ones which I can show you. You know, we're here long enough, I can show you some of these videos where he's zoomed in so far, you can literally see the bubble evolving out of a crack in the palladium.
So these are from his record.
Yes. Unedited.
Yeah. So see, we do something called glow electrochemistry.
Mm-hmm.
So when there's
Like Corona.
no, just
Oh, okay,
very
yes.
similar system.
Yeah.
When we have complete gas covering the entire electrode, the current suddenly drops.
Yes.
And then it continues to increase.
Yes.
We interpret all these things like as a normal electrochemistry.
Yes.
There is only H2
Yes.
evolving. And sometimes there is a thermal decomposition of H2O,
Yeah.
H2 and O2. How is he inferring hydrogen clusters? What is his reasoning for hydrogen clusters? Is it like, does he mean hydride formation on the surface or something more?
He means hydrogen clusters. And his very specific hydrogen clusters are this. Electron density leads to field polarization of protons, producing a positron and a neutrino, and the proton becomes a neutron. The proton and the positron and the electron get bound together with the neutrino into a neutral quasi-particle that he calls the iton. And the iton then forms an itonic cluster, a mesh, which then self-compresses the neutrons inside, leading to gravity decay, which he put on the front of his first book, which he said quad neutron decay in itonic cluster.
So I think probably I heard this from one of your videos. Messiat's
Messiat's
work is also similar? Or?
So Messiat's was in the 70s and 80s effectively discovering exotic vacuum objects before Ken Shoulders.
Okay.
But Ken Shoulders was very much more public because Messiat's was behind the Iron Curtain. Messiat's traveled and presented his work in America at a conference in 1996, and the guy, Hal Fox, that had bought the patents of Ken Shoulders came and told him, yeah, sorry you discovered this first, but we have all the patents, which are on the table over there, and we'll talk about them later.
He also talks about itons, or?
No, he doesn't talk. He calls ectons, and they're explosive electron emissions.
Okay, that's ectron.
And it's the same kind of thing. When you get a current density that is over, I think it is 70 amps in any structure. So if you go and look at Messiat's 1996 paper, literally every single way that all of the other LENR people have said that you can improve LENR was in that paper in 1996, and they've just reinvented the wheel over and over again. But it was all
is different from iton, or it's the same.
Okay, it's they're all the same, right? But his is an electron cluster, and with atoms in there from the host metal. Ken Shoulders says the metal or heavy ions in gas stabilize the electron cluster. He is saying it's a different type of structure, and he criticized Ken Shoulders in 2001. Do you want to sit somewhere?
No,
Okay.
I'm reading.
Okay. 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 He criticized Ken Shoulders' idea of an exotic vacuum object because there was no explanation how a plasmoid could maintain its stability and also the fields necessary. And he was right in that, actually. And there was a lot of attempts by Yin, I think, and also by Jin, rather, and also by Sarfati and by Hal Puthoff to explain various different ways that a plasmatoid, a plasmoid, an exotic vacuum object could bind together. And anyway, so they do, and there's a lot of theories as to why, right?
So do you believe that is this the only mechanism for NR, or one of the many mechanisms?
The process has a sliding scale of different things that it can do. And people are jumping on that scale at different points, and they're trying to explain what they see in there. If you look at this page, I think it's page 89, or it's in the first chunk of the book.
So this positron neutrino, which you mentioned, I don't have my hard copy with me, but
Okay.
I can look at the PDF. So where is this?
It's in the early parts of the book where he describes the structure of an iton. Okay. What am I looking for? It's in the first page part. Okay. So basically, he says that there are many things that he's observed here, and depending where you are on the level of intensity of your process, you will get things that look like fission. You'll get things that look like fusion. You'll get things that look like muon catalyzed fusion. You'll get things, so all of the above. This is a natural process which occurs everywhere in nature, and it does all of the things in nature to give us the crustal abundance we have. Okay? So
your opinion is this is a complete mechanism?
I'm saying that he recognized there's a lot of things that it does.
Okay.
And this was his best attempt at doing a flow chart. Like, if you exceed this, then this happens. If you go down this path, you have these options that can occur. Off this path, there's a branch that comes out here. And what he's doing is he's combining everything he knows. Because within his capacity, he left no stone unturned. He read past literature and analyzed the proceedings of his contemporary colleagues. So if I...
From what, Tesla times, or when?
He looked at everything. So here is 2019. It's the proceedings of the Assisi conference, ICCF26. This is typical going through his archive. He's literally ringed every paper as he's meticulously reviewed it, right? And he's gone through line by line. This is his notes. This is his analysis, right? And he's done that through all proceedings. And he's evaluated them on their merits, and where necessary, he's adjusted his own thinking. He hasn't said, I believe this is the theory of Lena, and I'm going to die with that belief, right?
I feel depressed now. I have so much more to do.
Well, maybe he will help you get to a shortcut, right? So he did this absolute pioneering use of videography, producing data that still to this day stands as some of the best in the field. Now, he believed that there was this thing, and he called it the NATO model. I've described how you get the itons. The itons then bind together into a cluster and produce a mesh. He believed this because of what he was seeing. He was seeing these kind of regular geometric things coming out of the system, and he was imagining that it looked like the fermented glutinous stuff that gets stuck when you have a natto bean on the outside, right? And this is a structure that was produced in an experiment. It's blown up.
Compositionally analyze that.
Yes, and these are the typical elements in Lena.
Yeah, see, for example, Randall Mills also seems to observe these filamentous objects. And
yes.
He calls it hydrino compounds.
Well, of course he does.
So
that's his bag.
We are also trying to reproduce those experiments. But compositionally, what are these?
If you go into this particular paper, this one here by Bogdanovich et al., he shows where we'll talk about this later, water flow plasma discharge, they produce monopole with a strand in between. And those are magnetic because they've got monopole ends. They got magnetic ends, right? And they have a strand of something. And it floats around in the video, right? These are the things that Mills thinks he's invented, right?
Yeah.
He may have done, but it's also in this guy's work from the early 2000s, right?
They might have also observed.
Yeah, of course,
yeah.
Right? But what I believe is going on here is, because we've seen this in extreme detail, is that within these macroclusters, it's fractal and the substructures, and they have these balls, and the balls can be of different materials. They can be silicon dioxide, they can be iron oxide, so on. And the material goes inside these balls through one end, and it produces a density that is ridiculous. And this is the only picture you need to know, because you have a lead sphere, and the volume of the carbon that's been synthesized inside the lead sphere is far higher than the inside of the lead sphere. So you do not need anything other than preschool understandings of putting blocks into holes to know that that isn't possible unless something is going on interesting with these carbon atoms. And that something must be that they are coherent in here in some way. That's it. You know that. So if these are the little balls here, right, then they are spewing out behind of them strands. And that's one thing that he observed a lot of. Strings. And the strings can be of the material in the experiment itself. So if I pull up probably one of the most important papers here, not that one, this one here, with the new scanned images, which you'll all have access to soon. This is also referring to the video that you've just seen. So here is your IV curve for your different phases, okay? Now you've got it on graph sheet paper from his original sketch. Here, these were black and white things that you couldn't see what was going on. You can see they're all purple, but these are purple and these aren't. And in this part of the video, he says, in an explosive event, the microsparks decoupled from the electrode, which was the cathode, and they moved towards the anode. And he says this means that they can sustain themselves in the water, plus that they are negatively charged. So he was already finding in 1995 in the experiments that these things could travel through the water and maintain their state as a plasmoid, not connected to the electrode.
But why can't it be a gas bubble?
Yeah, but it's glowing. It's producing plasma light.
So he had a black and white.
Wait. I'm getting to what I was going to show you.
Okay.
I'm just getting down there. So these are the radio emissions. They were frames from videos.
Okay.
And
his was black and white.
No, his were black and white in here because he was printing black and white.
Okay.
Right? Now we've got the video frames and we've taken images from the video and now we can see what they actually look like. Right? So you can see the richness of his data. Like, for instance, here, this is a spherical material taken out of palladium. We've seen this in so many experiments. What happens is the magnetohydrodynamic structure produces a non-radiating boundary, and everything inside that material disappears. And he saw that too. It's the principle of the 1920s technology called electro-discharge wire machining, which no one has been able to explain. And I took 90 seconds of taking a used brass wire electro-discharge machining thing, putting it under the electron microscope, and I see the scallop sections taken out. And then over to the side, there was the yin-yang structure with a sphere of carbon, a sphere of the brass, and then this wavy line coming down and carbon on one side, which is the ohm, right?
Okay, go on.
Okay, so
These
here...
videos are on your website, right?
no, these are all going to be part of what you're going to see. These are the traces you'll see, but here, these are the products. Now, in the book, you can't see what that is. You can kind of see. He says, very often in the experiments, you see these ribbon-like traces. These are ribbon-like traces, right? Okay. Now, the interesting thing is, he cropped this off and so on, and now you've got this much higher clarity here. That is what you're seeing now. And you can see that this is a hexagonal tube now because he cropped it off and you couldn't see it in the original book. And this is the structure. And you know what that is? It's almost entirely potassium, the electrolyte. The electrolyte has been...
Do you have filaments also with you? Or?
We've got filaments in different experiments from different authors.
Okay.
When I see this, I just see more of the same.
Okay.
But in this particular thing, the potassium, how is it putting out a whole strand of potassium? It's in a potassium electrolyte. Well, what it's doing is it's packing it into that sphere. At the center of the magnetohydrodynamic vortex, it's become coherent. And at the end of the time, it hasn't transmuted. It's just been captured, the potassium ions, and they've been spat out as a tube of potassium. And so that was in the sphere. And when the material came out, the substructures in there spat out little bits of whatever the material was in there. Now, if you get the pressure up to a higher degree, it'll start transmuting. So you have to bake it, yeah? And this is the fermentation process that he's describing in the NATO model. You create a structure in which you pack stuff, and you keep packing it, and you keep packing it, and that is like your maturing process, and then the structure breaks and other stuff comes out. In S.V. Adamenko's work, he says what happens is you get an electron gas, nucleon, which is bare because all of the electrons have been stripped off. Nucleus with all of the electrons stripped off, nucleon macrocluster. S.V. Adamenko, Controlled Nuclear Synthesis, Elsevier Publications, 2007. 20,000 sequential experiments worked every time. Transmuted and formed all of the elements in the periodic table, regardless of the metal used as the target, and on the accretion disk. And do you know what it did? It produced iron-rich crenellated spheres, which you're going to see in a minute. Okay?
So is this recording going to be posted on your website?
Yeah.
Okay.
Yeah. Okay. So what he found was in this core of the structure, which is made of different other stuff, in the core, you pack the nucleons, and if it breaks early, you just get out what you put in, right? Or you might get, if it's a very heavy element, fragments, and we'll talk about that later. But you might not get out what you put in, but you still get out normal things that you get in Lena, right? But if you keep packing it in there, Adamenko shows that you start to form iron. Once you get to iron, it keeps on iron for a very, very long time. If you go back to the George Miley, I think, his study in 2009, by far the most common element observed in all Lena experiments up to 2009 was iron. Synthesis, regardless of whether you started with light elements or heavy elements.
But we used to think that's because binding energy per nucleon. Iron is the
It is.
Yeah.
Yes, it is.
Yeah.
But you get to iron, and then what happens is you keep ramming stuff in there, you keep baking the cake and putting more ingredients in with all your chefs, and then it goes through a critical threshold of density of nuclear matter in the electron cloud, and then it starts shooting up. And Vysotsky was in here earlier, and he confirmed they even seen several thousand AMU.
So after iron, it gets converted to
It goes whatever you've got into the structure. It then starts to rapidly produce iron. It produces iron, 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 iron. There's a little gold, something that's 455 AMU, something that's 700 AMU.
Oh.
Yeah. Now here, this is what we were able to give him in the 20 minutes when we met him before he sadly passed away a month later. And these are replications of some of his findings by third parties in things that I had analyzed or third parties had analyzed. This is carbonized film that had been produced in his electrolysis experiments. This is carbonized film with iron, okay? Here, this is in a plasma reactor called Vega in Holland by my colleague Henk Jurjen. At the end of each of the carbon films on the zinc oxide background, when this overall structure blew up, you see an iron-rich crenellated sphere all over the place at the end. They're all over the place here. Little ones and big ones, okay? This is one of these ball lightning-like tracks. This, if it's the right material, will end up being iron. And I've literally got one of these in a Henk Jurjen experiment where you have an iron ball and you have a tornado coming out back made of iron as it's deconfined. This is in fused quartz in the Lion experiments. This is in boron nitride, the second hardest substance known to man. Cut lines this way and cut lines orthogonally to it. That's because of the structure of the ball lightning. And here, again, in boron nitride. Okay? This is in Matsumoto in 1993. This is in a George Eagley microwave plasma reactor that I analyzed in the aluminium. It's literally exactly the same size. It's exactly the same proportion. Even the bits here are exactly the same. Right? Again, this is the Vega experiment. This is an impact of one of these structures as a plasmoid on the fused quartz. And this is an example with the crenellations on the outside. And he would see these things as, you know, the bit that leads to the idea that it might be natto, you know, fermenting. This is in Roy Shinamaza cavitation, exactly the same boundary as his, with the bit inside with the bubble-like shapes. This is where he was thinking that these are these mesh that helps compress the matter. Okay? All right. So iron, but not necessarily. It does all of the above, and we'll talk about where it comes from. Okay. He was also not, so he changed, this is very important. He changed his position over time to match third-party evidence. So he took on new ideas. He didn't say, this is how it is, you invest in me and you're going to win, right? And then, 30 years down the line, yeah, we're getting there, we just need another 5 million, right? He changed his...
Are you referring to any particular person?
No. There's several you could choose, right? But he was also not afraid to deal with other unexplained phenomena. So this was an inquisitive mind outside of just low-energy nuclear reactions. This is a man that wanted explanations for things that people didn't have an explanation for. He's a man after my own heart. I don't want to know about how things work that I know work and whatever. I want to know about how the things work that I don't know how they work, right? And so he's looking at crop circles here.
Something about consciousness?
Yes. Actually, I don't know, actually. I would say he probably has. Because I haven't even read what is now 200 kilograms of materials. Okay? He learned from and presented to conferences outside of the Lena community. So when, in 1993, Ed Lewis sent him this letter, signed by Ed Lewis. Ed Lewis worked early, I think he worked with John Dash, but he worked with early cold fusion experiments. And he saw these things that seemed to transmute matter over time. And he said that they are normal, they're a new type phase of matter, a new type of matter. Whatever it is, I don't care what you call it, he's saying it was definitely a new, different type of matter. Okay? And it was the same thing as ball lightning. And in that pack, has sent him a marked up version of Ken Shoulder's patent. He sent him some Randall Mills material, some early letters from Randall Mills here and from other people. And he's basically saying that these are ball lightning. And what happened was, Matsumoto recognized that it probably was ball lightning, whatever ball lightning was, and he started mentioning it in his applications and works to fusion technology. And then out of the blue, the fusion technology changed the rules and said, you're not allowed to publish a paper and calling it fusion if you are not showing evidence of neutrons, gamma, X-rays, beta, right? You're not allowed to be heard. After he mentioned ball lightning. The same thing happened with Ken Shoulders. In the early 2000s, you started calling it ball lightning, and then someone, who I won't name, but they worked for Los Alamos National Laboratory, they stepped in and demanded that all of Ken Shoulders' work in 2003 be removed from the Linecanna database. Jed Rothwell was very upset about that, but it was done. I have the emails where Ken Shoulders and Mitchell Schwartz are complaining because both of their papers were asked to be removed. Mitchell Schwartz because they wanted to put a secrecy order on his devices, his nanos, which he had a conversation with me in Missouri, ICCF26. Yeah, he complained about that to me, but it took him 10 years to get the secrecy order removed and for his patent to go forward. So his material was then allowed to be on the Linecanna database, but they kept the stuff from Ken Shoulders off. So when you mention ball lightning, no, disinformation, misinformation, limited hangouts, they're all thrown on you, right? So someone knows something about ball lightning that you're not allowed to know. Okay.
So from whom was this request coming?
I said, I'm not going to say, but they worked at Los Alamos National Laboratory. There we go. Because I'm putting this out on YouTube. Hello, YouTube land. Okay. They will answer in heaven shortly, probably. Don't wish that on anyone, but it's a matter of time. Right, okay. So this is a little bit about who the man was. The man was a pioneer. He was a radical. He was a free thinker. But he was a meticulous worker. He did not leave any stone unturned. Right, so out of the new material that we have going into the remake of the book, as I said earlier, this up here, honestly, I wanted to learn from him. I really did. But when I was looking at some of these images in the book, I was dismayed that I couldn't see what he was saying I was meant to be looking at, and that was giving him the justification for what he believed he was seeing. Firstly, as you can see, if we go up here, it's going to let me do that. It's going to let me do it. I couldn't see the colors in these, okay? And this tells you a lot of information. In some of the images where he's showing it working, I couldn't see anything. I mean, like what?
Which is the paper where this negative clusters migrate?
It's in this one, yes.
Okay. Which page is this?
This is page, in the original, the 1-for-1, it's 214. What I've done in here is I've used the space to improve the layout, but I've kept it the same page numbers essentially for each major paper. Okay. But on here, he's talking about that ring clusters are formed on an iron cathode. Okay. And I could kind of see ring-like things, but it wasn't convincing to me. I couldn't correlate it with anything because it just wasn't enough detail. Okay? And here he's saying this is an intermediate stage of the cluster decay. I can't see what that is. Well, here's what we have. Those are very clearly ring clusters. Right? Now look what he says. These are his quotes from his book here. When the iron wires were used, because he used titanium, palladium, nickel, blah, blah, blah. But when the iron wires were used for the electrodes, tiny ring products were successfully caught on the surface of the cathode. What does that tell you? What does it tell you? Well done. You were here earlier. They were cheating. Yes, they're magnetic. Right. You can see similar structures being caught. So we have on video the production of a toroidal plasma with the cone vortex coming into it. And then periodically it decouples from the tube in which we generate it, and it heads towards the anode using the field between the cathode wall and the anode sheath. It hits the anode sheath, which is fused quartz, and it leaves marks that look like this, but splattered on the anode sheath. If you go to this QR code, you'll see them. I've got them in beautiful 8K incredible microscopy, so you can see they're hexagonal and pentagonal typically, but mostly hexagonal.
They're on your website.
Yeah, so you can go to this and you can go to the exact link. Okay, so this is a ring cluster. Then this image below, which is the one that I couldn't see anything of here, is an intermediate stage of the decay in which the inner circular zone still remained. Okay, so it goes from that to that. Now here's the rub. After a few days, the ring products all disappeared. In place of them, only the hexagonal products remained. This suggests that the ring products decayed to the hexagonal plates. So if you look at your product of your experiment after 2 days, you're not going to learn everything about your experiment. You need to get it dry quickly and get it under analysis, hard, deep analysis.
In 2 days, it was kept in the electrolyte or outside?
For 2 days, it went from this through this intermediate stage to
It was
that.
kept outside or in the electrolyte?
Outside.
Outside.
Yeah. Because he had to analyze this to get this image. That wasn't in the electrolyte, that's under the SEM. So definitely not in the electrolyte. Not going to work in an SEM. You're going to get full of gas, right? So this shows that whatever this was is able to sustain for around about 2 days. Now, I only chose 3 examples because there are so many findings by so many authors across the world in independent experiments across the decades, right? So I chose 3, which I've given the QR codes for down here. Monopoles bound to iron 57, iron, that's why I chose that one as the first one, decayed after 2 days. In Leonid Orytskiev's exploding titanium metal foil in water experiments. So he has titanium foil in water, inside a polymer, inside an aluminium chamber. He goes, produces a ball lightning above. A few microseconds later, it produces thousands of little micro ball lightnings that come off outside of the chamber, which he has a mirror above, so he can picture it here and picture it from top down with the mirror. And then he sees 0.7 meters away from the experiment that's there, he has an iron 57 sheet here, another iron 57 sheet here. He has a standard ferrite magnet on the back with a north on it, standard ferrite magnet with a south on the back of the sheet. And then in another room, he has another bit of iron 57. And he looks at the NMR on those, and one is shifted one way, the other one shifted the other way from the control. Which means certain poles were attracted to the iron 57 because it's iron and these structures are magnetic, that bind to the nuclei, not these scale, much, much smaller ones. Not these scale, smaller ones, right? And they bound to the iron 57, but they decayed after 2 days and it went back to the same as the control, right? This one here, observations of long-lived toroidal plasmoids, that is plasma toroids, by Bogdanovich in discharges through water jet. There's a lot of discharges in a water jet kind of thing going on here. Lasted for around 2 days. Water jet onto water, onto a metal plate. Extreme hydrodynamic shear at the point of connection between the two. DC bias, pulse discharges, right? Produced dark plasmoids, white plasmoids, pinch tornado discharges, your monopoles moving around with the filaments in between that you're describing earlier. But take metal plate away, look under microscope, see toroidal plasmoid structures glowing, emitting light, moving around on the metal for 2 days. Somehow it is stable for 2 days. Reductions of the ability of the medium around Anatoly Klimov's plasma vortex reactor, the same thing that the N-Gates technology is a derivative of, to pass gamma rays lasted for around 2 days after the experiment. That is to say, plasma vortex reactor, something in the medium around that reactor out to a certain distance was extracted such that a gamma ray source could not pass the gamma rays that were being synthesized. Something is, and this was actually by the guy that did the first boiling water reactor in the 1950s. And what's his name? Can you remember? The guy that went on to do the cold fusion in Russia after, and he ended up going into a gulag because they didn't want him talking about Krypton-85 coming out of RBMK reactors. Damn it, I can't remember his name. Anyway, that guy, he said that his palladium deuterium boiling water reactor from the 1950s that was done under classified research produced some form of radiation that Filomenenko. Thank you very much, Ivan Filomenenko, right? He observed a form of radiation that changed radioactive decay rates, but also that with this understanding, he could produce a technology that prevented the transmission of radiation, so they could create radiation shields. And this is basically what he showed recently, okay, for 2 days. So something in all of these systems is doing what was observed by Matsumoto. I believe it's exactly the same phenomena, okay? This is one of many, many examples where he is first, or he provides not ethereal, I think this is going on. Of course, this work is absolutely brilliant. But he's literally showing you the physical evidence. Now, there's another one. In this data, unique use of nuclear emulsions showed that ring-like products could act as neutral structures that could walk through matter. This is in this 1996 paper. The traces, this is his words, the traces suggested that some particles walked around on the surface, this one here. The figure to the left, that's my words, just because I'm a brevity, shows a ring product left with a rail-like trace. Ring product, rail-like trace. This clearly indicates that the extraordinarily rail-like traces were generated by the ring products that escaped from the cell and walked around on the surface of the first nuclear emulsion. Nuclear emulsions, like I show you up there, outside of the cell. The diameter of the ring was about 10 microns, which was approximately the same as that of the ring products observed on the iron electrode. This observation suggests an extraordinary result, that the ring product could penetrate through the glass wall of the beaker and the water solution. So the ones that didn't get stuck here, that you see over there, some of them are able to travel through the water, through the glass, through the air, through the containers, onto the emulsion and leave it. But he didn't labor the point. He's not even showing the data for me that's even more conclusive than what he just said. It's this. What do you see here? What shape is that? Hexagon, right? Do you see anything notable about this hexagon shape? It's got like triangular pie slices, right? But like 120 degrees, 120 degrees, 120 degrees. Look at this. You've got a 120 degree division there. This is definitely this. Absolutely. That's my addition to the money shot. That is what is happening. This was in 1996 that he published this. It wasn't until 2010 in an interview between John Hutchison, Ken Shoulders, filmed by Nancy Lazarian, John Hutchison's wife, that Ken Shoulders said, you can get these exotic vacuum objects into a state where they can just walk right through things. He did this in 1996. Ken Shoulders discusses it in 2010. So far ahead of the game. That one paper, there is so many things in that, like one line in that paper is a new discovery. And it's just almost a throwaway line, over and over and over again in here. It's seminal work, ignored by the learner community, with hard physical evidence that they do not, this is an X-ray film, this is one of these emulsions. They don't even know how to do it. They can't even have a comment on it because they are incompetent when it comes to the main means by which your grandfather was able to do this.
So perhaps at the time, or even now, the learner community was, the focus has been on just heat, not these kinds of transportation. Perhaps that is one of the reasons why something more interesting has been neglected, perhaps.
But they're missing the point of how it does the heat. All energy comes from a change, a reduction in the distortion of the physical vacuum, right? So if you're taking a deuteron and a deuteron and you fuse them to helium, Let's say that distorts the physical vacuum by 1, this distorts the physical vacuum by 1. When you fuse them, the combined thing basically distorts the physical vacuum by 1. If you take atomic hydrogen, you make H2, the physical vacuum distortion of the molecule is less than the two H stars, the H with an electron, right? The proton with an electron. So that's chemical energy. I've described nuclear energy before that. So if you are taking tungsten and you are making calcium and xenon, or you're making all the elements in your body, like happened with Ruy Shinamaza on the tungsten welding rod, we made all these new elements which weren't there before, like instantaneously. And if they are all lighter than tungsten, you can bet your bottom dollar that there's a good chance that that produced actual excess heat. Because, or energy, which might have been photons or energy in forms that were coming out. Now, in the work of S.V. Adamenko, the combined total of products that they observed coming out of their discharges in transmutation, in the strange radiation tracks, in photonic emissions, it was 10 to the power 3 over the input joules put in to produce the discharge.
So I don't disagree with you. See, many times it's been taught here, right? The correlation has been with light element transportation and heat. Hardly anybody has correlated heat with heavy element transportation. This is unfortunate.
But the most important data, in 1996, from Mizuno, where they saw a COP estimated at 800 times, bigger than anything you've seen here, and exploded and would have been a death blow if anyone had been close, was with a tungsten electrode. Tungsten is key to many of the key elements. So when Sapphire Group in 2019 presented their heat-producing thing, they showed the products. I went onto the MFMP's programmed by Philip Power based on Alexander Parkhomov's data, free reaction calculator. I typed in their products and said, what was the starting thing? And it said tungsten, right? Right? So I wrote to them and I said, I think you're using tungsten as part of your fuel. And I said, you need to be aware that this will produce strange radiation, and therefore you need to account for that. Then I've been helping them understand and protect themselves from potential radiation that might be coming off.
So what is this calculator you mentioned?
It's called nanosoft.co.nz, and it does 2-to-2 reactions. So there's like 1-to-2, that's fission, 2-to-2, which is nucleon exchange, and 2-to-1, which is fusion. It's still about 1.3 million potential calculations. They all have to be net positive, and they all have to not produce a radioactive material, right? And I've sat in almost anyone's lecture, and I can type in what they're seeing, and it's the most likely product to come out of squeezing something into a small box. You just need that one piece of logic, which in my poster session in ICCF26, I said, this is squeezing stuff into a small box. And I meant the smallest surface area for a defined volume is a sphere. So when I was saying a small box, I was always meaning a sphere. I was meaning a sphere-shaped box, which people have a problem with, but actually a box can be a sphere. And so you're crushing that thing into there. And so the more pressure you put on something, the nuclei have to arrange to a lower distortion of the physical vacuum to answer the pressure that's being applied to them. And that's why ultimately you go iron, gold, lead, uranium, somewhere up there. Yeah. And so, this is a real pioneer. And what we have in the room here. Okay. Now where's me? So this was his pre-Lenna. I've spoken about this, about how he got introduced to ball lightning. He then met George Eagley, and he started presenting on ball lightning here. Now, in his work, he found that this kind of image was used for his belief that it was the shock wave that's produced from quad neutron decay. In 2001, he apologized to the fusion community in a letter to Fusion Technology, saying that initially he thought it was quad neutron decay, but he said later he realized that microns to millimeter levels of matter could simultaneously collapse into new nuclei, and predominantly carbon. which is what you get out of the systems. You get predominantly carbon. And it's not necessarily collapse. It might be cluster decay, which we'll go into on my poster session. So and this is where you're definitely never inventing anything new, because here, I go like this, we can show this up. He says the old theory about what was going on with the Earth and the Sun was going around the Earth. That's the Ptolemaic theory. Then you have the Copernicus theory, where you have the Earth orbiting around the Sun. He says, how the hell do you get two neutrons to fuse? Okay? And he says, well, maybe you need the man to orbit or something to orbit around them to get them to pull together. And that is exactly correct. He says that this is the Big Bang, and he says this is the mini bang. And in that one phrase, he's reframing this as creating a new universe. And that's what happens inside the core of these structures. In these structures, you get the literal bit before hadrons and baryons form. And he has here, in some of his images, so this was his original cover to his first book, Gravity Decay of Quad Neutrons. And again, this is part of his technique. He would use the microscope objective with film. He would take photographs, he would print them, and because it's plan objective, you could stitch them together and produce these large. I actually have this, it's about this big, this composite shot here. This is Hawking radiation from a black hole, tiny black hole. Absolutely critical to this process, in my view. This process relies on black hole, and I believe consciousness also, I think when your consciousness spins up, you're creating little black holes in your brain. I genuinely believe that.
SEM images.
Yeah.
SEM, electronic microscopy.
No, this is on nuclear emulsions and then photographs under X-rays, so under a microscope. So you can use nuclear emulsions to see the black holes decaying. Now, in S.V. Adamenko's work, they observed things where under secondary iron mass spectrometry, they were firing in the heavy iron to knock off some atoms to determine what was there through the drift, right? But they didn't see the secondary ions. And then they noticed they weren't even seeing the primary ions, because you should see a shed load of those in the signal, but they didn't. And then they turned it off to find out what was going on, and on the phosphorus screen, they saw a glow from the center of this spot that they couldn't see any atoms from, and not even the atoms that were going in, and it exponentially decayed. And he calls it a black hole. This is S.V. Adamenko. And the glowing is the consumption of the primary ions that they are shooting at the structure that was formed in the process of controlled nuclear synthesis. He then found around that central black hole, there were regularly spaced spots, which were smaller, where the same thing happened. If you fired primary ions in, you didn't get any secondary ions, and they ate the primary ions, and you got an exponential decay on the glow, right? So S.V. Adamenko was seeing black holes, which persisted in the metal. How do they persist in the metal? Because the metal provides them electrons, and it provides them baryons. It's constantly feeding itself. If they persist, in my view, which I'll talk about in my presentation on Thursday, in my poster presentation, the black hole itself causes color disconfinement of baryons, and they produce a quark-gluon plasma, specifically an electron quark-gluon plasma. The quark-gluon plasma is the most superfluid thing known to science, and it produces a magnetohydrodynamic vortex which maintains the black hole, which other matter can be pulled into, and it's self-feeding. That's when it becomes lasting for 2 days. The payload that allowed that to exist, it burnt itself out after 2 days. And then it starts to collapse back to the material that was originally there, or synthesized material. If you keep feeding it, and it keeps pulling material into the core, it will go into these structures, and they will spew out as largely carbon, because it rips matter apart, and I'll explain that in my talk. It rips matter apart, but if you keep feeding it, it'll then start making up to iron, which is why in almost every experiment, if you actually bother to look, you'll find these iron-rich crenellated spheres, which are hollow. But if you keep going, then it goes beyond that. In S.V. Adamenko's patent from 2003, the key image is a pure copper 5/9 plate. He then has a spherical, broken off hemispherical iron structure, and it's got a perfect hemisphere inside. In 2005, he said, inside that hemisphere, that empty space, that's where the nuclear reactions occur, and they occur due to dark matter. And the dark matter is able to be pulled in, specifically the relic neutrinos, which speaks to Alexander Parkhomov's understanding of what's going on. It gets pulled into that magnetic core. When the thing dies, it spits everything out because the electromagnetic quark gluon plasma that confines it in that core dies. It doesn't have the magnetic confinement, which is what is described in the first page of Matsumoto's book, and it spews out all of the synthesized or other elements that had been put in there into a coherent state. And that's it, really. Matsumoto had it, and if you've got any questions on any of the materials, over here, when I first went to visit the house of Matsumoto, I'd been buying time with Sho and filling our days whilst we got an audience with your father. And I was seeing owls everywhere. And when I went into the lounge, there were these two things on the mantelpiece. Yeah, these two things on the mantelpiece. And I thought, you're freaking kidding me. Because this is the model of the technology that runs the universe, the hydrodynamic vortex, which is the magnetohydrodynamic vortex when you have charged particles. It is the symbol of Delphi that shows the understanding of how nature works in the place where everyone in the ancient world used to go when to go to war, when to plant their crops, when to have a baby, and the epsilon, double epsilon, which is the symbol of ball lightning on the ball lightning coins from Macedonia, that is a circle and a half circle with a line and a line through it, which is the symbol of ball lightning on their thunderbolt coins, right, pre-Christ. Okay, and so
You also have your 120 degrees in there too.
So you do. So the family have very kindly given this to me because it means more to me. And then if you want to make a bid on these are Matsumoto's in his latter years. He decided to paint little reading stands for you to put your book or your tablet on. And these are his work. They unfortunately only the subject is given and the date, but if you wish to put a bid in for one to help support, and I think you should have the money if that's okay by you. All right, I've already got one sold, so then I'll be very happy because it means I don't have to carry them back to Europe. And so Hiroka-san has agreed to sign them, and I will sign them if you think that's useful.
Handmade.
They're handmade. So if anyone's got any questions?
Where did the iron go?
What?
The disappearing iron. So I didn't quite understand.
Where did
that.
the iron go?
Yeah, the iron.
I don't know whether this is iron. So actually on this paper, and this is beautiful. This is just a nugget pulled from 1996. This is the analysis, which you can now see. But he says that it produces iron on palladium. It produces iodine. And he says that you can get to iodine from palladium plus hydrogen proton plus oxygen 16, right? But if you fuse oxygen 16 with palladium, it's negative 0.3 million electron volts or something. If you fuse, you need to listen to this, Bin. This is for you. I'm doing this for you. Okay, I'll start again.
Yeah, okay.
On palladium, he saw the synthesis in these ring clusters of iodine. Not anywhere else, just in the ring clusters, okay? And he surmised that to get to iodine, you need to take palladium specifically from the Parkhomov reaction table. It is the only option that is possible, and it's with palladium 110. And you need a proton, a hydrogen nuclei, and specifically only one hydrogen nuclei, and oxygen 16. But if you take oxygen 16 and palladium 110 and try to fuse those, it's a negative exothermic reaction. It's not going to be possible. But if you take the proton, make oxygen 17 simultaneously with fusing the palladium 110 nuclei, you get to iodine, and it's about 4 million electron volts net benefit. So he observed what you have observed in 1996.
in palladium.
Palladium.
But in our case, we don't have palladium.
I know you don't have palladium. What I'm saying is it's a synthesis of oxygen 17,
Yeah, 17.
which gives you the yield from water, which is in his reactor, that allows the progression to synthesize a heavier than iron element from the palladium source.
So all 17 is intermediate.
Yeah, and we've described why, because H2 has no magnetic moment. This is a ridiculously, stupidly magnetic structure. It's not very magnetic far away, but it goes like off into practically infinity for all intents and purposes when you get close. So if you split water with an electrical discharge and you've got some protons flying around there, or your protons and the electrons, the atomic hydrogen, they have a magnetic moment, both of them, slightly more with the electron attached to it. It is oxygen in O2 form, which is 17,000 times more paramagnetic than a proton or a proton with an electron. That gets pulled in because you're also splitting that, particularly when you're doing AC, which he did a lot of AC, and which you do when you're producing mixed oxyhydrogen gas. Okay, that gets pulled in, the oxygen O2 or the O minus or the O3 gets pulled in because all of them are paramagnetic. It's unique in that respect. Gets pulled in, the hydrogen gets pulled in, and it produces oxygen 17. Oxygen 17 also is a spin nuclei. So it's preferentially caught in that vortex loop now. And so that is why I believed and I suggested that it was the intermediary in your reactions. I hadn't read this. I hadn't worked out that Sundaresan and Bockris was doing the same, and ad infinitum. Like when you actually go and reanalyze people's data, you see that oxygen is key. And Randall Mills, oxygen is the catalyst. I add water, I go bang, oxygen is the catalyst because it's uniquely paramagnetic. And it can go in all of its forms into the magnetic structure that's formed. He will see transmutation. He says there's no transmutation going on, but I don't know how he's got his own private universe where he does high DIDT discharges in a water-rich or hydrogen-rich environment, and he doesn't see transmutation. It's just no, sorry. It's just a narrative. Okay, that's that. Any questions?
Remember
Yeah.
the story I told you of Roger Stringham back in Fort
Go on,
Collins?
yes.
And I asked him the most amazing thing he had ever seen in all of the years, and he talked about the case of going on vacation and coming back and starting to turn on his ultrasonic power supplies, and a little ball lightning emerged out of it and proceeded to, he used the term like melt, he thought, the equipment. So he batted it off, and it didn't hurt him, but it went across the room and out through a glass window, which of course through the glass wall of the beaker, right, sounds sort of familiar,
Mm-hmm.
you know. So anyway, then another one emerged, and this had been equipment that had been shut off for weeks.
Wow.
And so he wasn't even powering up, he just starting to do it, but hadn't really turned on the outputs. So that chased out the cobwebs of these little ball lightnings.
Well, here's the thing. Ken Shoulders says these structures can live in metals indefinitely.
Right.
How? Because they've got a ready supply of matter to keep them operational. Now, they probably go into a dark mode, and Ken Shoulders then said, I can deliberately force them to become active again, and then they blow up, and as mean as nasty as you can imagine, or mean as nasty as can be, is his particular phrase. The same structures are in Bin Huang's reactors. Unimaginable volumes of them, doing their magic, okay? And they can get bound to iron in this case. You have some iron components in your reactor, they're going to be there. When I approached, the first day I went to, the first conversation I had with Henk Uren when he approached me about the Vega experiments, he described it, and I said, what are you making your reactor containment from? He said, stainless steel. I said, you need to make that into mild steel. Because you want this to happen, gets and stops. You don't want it coming through and going into your body. Mild steel is your first point of trying to fix this. Now, I argue that you are making a literal exotic vacuum object. So Ken Scholder started off with electron beryllium, which is a strong electron. He then moved to charge clusters because he realized he was able to transport protons or whatever it was alongside the electron clusters. Okay? But then he realized they seemed to do this kind of thing. They were walking right through things. How would that be? Well, he describes the fact that the charge goes to 0. Well, actually, he doesn't quite say that. He says, I can take 100 billion charges and make them go to 1. Now, 1 charge, but it's micron across. Well, is that resonant? Like, people talk about neutron resonance by having neutron resonant modes in resonant, like boron or gadolinium or, indium. It has resonant modes for the neutron going in, so it can be captured by the material or moderated by the material. Okay, so there's resonance. I do not go through the floor because my electrons are all the same as the electrons in the floor. And so there's perfect charge repulsion. A normal electron, a normal proton, and a normal neutron are standard vacuum objects that live and breathe, as does atoms that are clusters of these, in our normal vacuum state. But an exotic vacuum object is a structure that's built in the same way as the normal vacuum objects, but they are much larger. They live in their own phase space. And so when they try to walk through this glass, the electrons on here do not see the wave function of the cluster. It just goes through. It goes through an aluminium hull of a plane. It goes through whatever this was going through. It's still magnetic. It can still, and these things are always bound 50% into the structure. In Binchuan Huang's system, it doesn't matter whether they're on this way or this way, and that's the ways they come. They're either 90 degrees to the metal or they're flat onto the metal. Doesn't matter. They're always 50% into the metal. Because the internal structure, if it goes further, it wants to push out. If it comes out, it wants to stick back down. And this is why you see classic plasma tufts, or balls of fire, as they were called before sapphire came along, right? In early papers, they're a hemisphere. Because the underlying toroidal structure that drives the non-radiating boundary, which is the hemisphere that you see, is 50% into the structure. So you see a hemisphere. But if you have a foil like we did as your electrode wire in some of the Vega experiments, you see a hemisphere this side and a hemisphere this side. You actually see both hemispheres. And so you see a sphere at the end of the wire. So, yeah, basically ball lightning can live in the metal. When you turn on the power, you excite it with electricity, and the structures go into their white mode, and they are energized up, and they move around. What could have happened is that particular structure, right, it was aggregating during cavitation, because cavitation produces these structures. It's almost the easiest way. So if you look at some of our ultra experiments, you get a yin structure, which has a cavity with a peak and a peak with a cavity in a perfect yin-yang ratio. And in one, you have a hydrodynamic vortex that's going around like this, but you also have it going around like that. It's multi-axis shear. And when you look at the polar molecules of water moving around in these two directions, you end up with a toroidal moment. You end up with two currents. And then that produces, with this one and the anti-one, that produces that structure, which produces a toroidal moment that comes out that way, which rips matter into the core of the structure. And you can see it. And a child can do it. A 3-year-old can do this experiment in 7 minutes. And so cavitation does exactly produce these things. It's the easiest way to do it. That's why I railed against the fact that it wasn't even mentioned as a way to do experimentation in this field. My first comment of the season here. And it will produce those structures that will come out, and they will bind to the metals, ideally the iron in the system, and maybe get energized later. So totally consistent with the understanding. Thank you for sharing that anecdote. It's a really important one.
Do you think, sorry.
Oh, hold on. I'll give you a battery. Carry on. You can ask the question.
Do you think all 17 magnetic strength of all 17 is all the same?
I think each isotopes have subtly different properties.
Bob would probably be wrapping up.
Yeah, okay, thank you.
Yes,
thank you.
Thank you so
Thank
much.
you.
I mean,
Pleasure. Yeah,
everything
thank you.
you
Thank you.
say is
Thank you.
always a great experience.
Oh, thank you, Dennis. That really means a lot coming from you.
You know, It
Yeah.
really is, and it makes me think about other things and other places, you know, like 64, the flagship of Energetics Incorporated, used ultrasonics to cavitate aluminum foil, no less.
Well, aluminium is the best fuel, actually. Yeah.
And so,
Single isotope, paramagnetic, unique amongst the
and
conductive
then they
elements.
turned around and used that with palladium,
Yeah.
not thinking about that.
Yeah, right.
They cavitated aluminum foil as the first step unintentionally.
Yeah, they probably
There
loaded
may
up the
be
system. That's it.
that it was those
49% of Castle Bravo was aluminium.
floating around left in the-
49% of Castle Bravo was aluminium.
Yep.
熱意がすごい。
The idea with this conference is we're going to show actual LENR real time in front of the attendees. We're going to show electrodes, no transmutation, do the work. They can see it under the SEM, do the experiment. Yeah, you should do. You should do.
You should.
Really. Do the experiment and then see the transmutation after the experiment is over. So within a couple of minutes, like maybe 20 minutes, you'll see raw materials transmuted.
What is that?
Yeah, probably less.
Maybe.
Come on.
Thank you, guys.
Just the right timing for
Check
the
a
battery.
public.
Wonderful.
Well, I
Yeah.
have a question about something we found unusual.
Go on. I like
Our
unusual.
experiment.
Yes.
We have
Do you
plenty of
think
time.
all 17
I'll think about it.
magnetic strength
Yeah. Absolutely.
Don't take so
Thank you
long.
very much,
Take
guys.
so long.
magnetic strength
100%.
of all 17 is all the same
No, I don't think they are.
down.
No.
Why? Why?
Well, firstly, it's got spin. With the other nuclei, don't.
But all 17 is a well-defined element. How can you?
Yeah, but oxygen 16 and oxygen 18 don't have, they're not spin nuclei. So you've got a magnetic component in addition to the oxygen normal paramagnetic nature.
But 17 has a paramagnetic,
Cheers, mate. Nice one.
has a magnetic strength.
Huh?
But it varies or keep the same, all 17.
O17 itself varies, or do you mean that it varies from the magnetic properties of O16 and O18?
No, I mean, all 17 itself,
It varies.
the strength of magnetic strength should be the same, right?
No. Because very small structures of these will bind to the O2 molecule. So you can increase the magnetic strength of oxygen, and likely oxygen 17 is better at capturing the structures. The oxygen itself collects magnetic monopoles. So then it changes its magnetic nature. This is done by Oroitskev. He says that this is the explanation for the different spectral lines above Chernobyl. The glow that thousands of people saw in Pripyat. He says the monopoles came out of Chernobyl reactor and they bound to the oxygen in the air, changing the spectral lines. Because it changes the electron positions. We've got to clean up in here.